All right. Let's see here. Good afternoon, everybody. Weeks are winding down. We're almost done. Speaking of weeks winding down, I want to talk about the syllabus real fast and some slight changes that have been made to it. Changes that I think most of you will probably like. But today we're going to be finishing up correlations. It should be a relatively short lecture, give you some time to work on assignment number 11 if you haven't done that already, which is due, I said by 3 p.m., but you have until the end of the day to do it. I'll make sure to change the due date on that. Thank you to everyone who submitted it on by Saturday. You got, I think, like 5 extra credit points that I threw on. Yeah, so good job with that. So today we're going to finish up talking about correlations. Then tomorrow, tomorrow on Wednesday, we'll have another shorter lecture where we're going to talk about some advanced analyses just beyond correlations. Nothing that you're going to be expected to really know how to do, just going to talk a little bit about some advanced analyses looking forward in the future. I'm going to give an overview of the paper. Uh, for the most part, we're almost done with the paper. We still have one more section to discuss, which is the discussion section. So we'll talk about just the paper overall on Wednesday, as well as zoom in on this, as well as the discussion section in particular. Then this coming Friday, no class. We don't have class this coming Friday. Then next week is going to be all about introducing presentations. So one of the things that you're going to have to do is with your group, do a about 10-minute presentation. Don't freak out too much. We'll give you a lot of structure. Should not be that hard. Anyways, going to talk about the presentations, give a really brief overview of the presentation, show you some templates on Monday, allow you to get in your groups to work on them. Then Wednesday and Friday of next week are optional classes. Come to class, there's dedicated time for you to get in your groups and work together in your groups. But if you want to work separately and you don't want to come to class, perfectly fine. On Friday, once again, another optional class. Come and work on your presentation if you'd like to, or ask me any questions about exam number 3. Or not exam number 3, excuse me. That should say the final exam. The final exam, which is that following Monday. We talked about, hey, the final exam is going to look a little bit different. I'll talk more about that on this coming Wednesday. Actually, I'll talk a little bit about it today as well at the end of class and show you an example of what you're going to be doing. But anyway, so on that Monday is that final exam time, but we'll talk more about that later. And then that Wednesday and Friday, I've broken it up so that way groups 1, 3, and 5 present on Wednesday, and groups 2 and 4 present on Friday. Once again, 10-minute presentations shouldn't be that bad. And then your final paper is due at the end of that week. And be on the lookout. I'll send an email out at some point, talk more about this in the next week or two. But there'll be extra credit points for turning in your paper early, but I'll talk about that in the coming days. Anyways, just wanted to throw this up here, talk about what's happening. No classes coming Friday, optional classes next Wednesday and Friday for you to do your presentation prep, and then come in on Friday if you have any questions about the final exam. Any questions right now about the syllabus before we jump into correlations? Chat. All right. Well, if you do, feel free to email me or stop in after class. So let's finish up correlational studies today. We just have a couple more things to talk about. So the first thing I want to throw out in using the direct message in chat, what is the answer to this question? As a person's consumption of vegetables increases, their body weight tends to decrease. This is an example of a blank correlation. Is it weak, strong, positive, or negative? Go ahead and throw your answer into direct message in chat. All right, I'm seeing Most people have the correct answer, which is negative D. It is a negative correlation, but I do see some other answers. I see someone say, a couple people say B, one or two people say C. So yeah, so first off, why is it a negative correlation? Well, you got to think back into that logic of, okay, well, what is a negative correlation? As one variable goes up, the other variable goes down. That's what the relationship looks like. So as one variable, consumption of vegetables increases, the body weight decreases. Negative correlation. There's nothing here that talks about strength of the correlation. We'd have to give you the R value or the R squared value. If you haven't watched that mini lecture, make sure you do that. It's up on, I believe, last classes in that folder. There's like a mini lecture, or maybe it was a class before that, talking about that coefficient of determination, that R squared. Make sure you watch that. I think it was pretty clear that some people didn't watch it because there was like a question or two on that quiz that was due on Sunday that people got wrong. So make sure you watch that mini lecture. But yeah, so this is a negative correlation because as one variable goes up, the other variable goes down. All right, question number 2. Of the following, the correlation coefficient indicating the strongest relationship is what? Is it -1? Is it -0.2? Is it 0? Or is it 0.8? All right, so I'm seeing split answers between A and D. And a couple other answers for B and C, but majority of people are saying either A or D. Can someone tell me, so the correct answer is A, -1. Can someone tell me why it's -1 and not D, 0.8?
Because you're going to square the 1, which is going to turn into positive, and that means there is 100% like relationship correlation.
Perfect. So whenever you're going to square this, and also you don't even have to think about the squaring it, which you are correct, Amina. You do square it, but just think about the absolute value. So just get rid of the positive or negative signs. Remember, positive or negative just tells you if it's a positive or negative relationship. The actual number itself, forget about the negative or the positive sign. The actual number itself tells you how strong that relationship is. And going back to that mini lecture, so do make sure you watch it. That mini lecture talks about, okay, well, how do we find out this effect size, which we'll talk a little bit about on Wednesday, but how do we find out the strength of the relationship? Well, you look at that square it, or you look at that absolute value, and we know that 1 is greater than 0.8. So that is why A, even though it's negative, remember that negative sign just tells you if it's a positive relationship or a negative relationship, but the number itself, the actual numerical value, tells you from 0 to 1 how strong that relationship is. And numbers closer to 1 indicate a stronger relationship. So 0.8 compared to 1, 1 is bigger, 1 is a stronger relationship. It's actually a perfect correlation. All right, so hopefully that helped clear up some confusion. All right, so far, let's kind of summarize these 2 questions and really what a majority of last class was about. Correlational studies examine that natural relationship between 2 variables. The correlation coefficient can vary between -1 and +1. The sign indicates the direction of the relationship, whether it's a positive correlation or a negative correlation. And the absolute value of that reveals the strength of the relationship. So forget about the positive or negative sign, just the number itself tells you about the strength of the relationship. Then this is the callback to that mini lecture that everyone needs to watch, that I recommend, a couple minutes watching. This coefficient of determination, this R squared value. So it varies from 0 to 1. And this shows the proportion of the variability in Y that can be explained by the relationship with X. Once again, watch that mini lecture. And it measures the strength of a relationship, this effect size, which we'll talk more about on Wednesday, in understandable terms. So once again, what you really need to know, that negative or positive tells you it's of a positive or negative correlation. And that number, which ranges from 0 to 1, that R squared value, tells you the effect size or the strength of that relationship. All right, seen this slide before, just going to have it up there. Correlation does not imply causation. We just use correlations to describe relationships, not to explain them. Those are for other analyses, which we'll talk about on Wednesday and in 204. So even if it's a strong relationship, a correlation does not mean that one variable causes the other. So this, you've heard it throughout the entire semester, correlation does not imply causation. I still say it multiple times because there's still people in their analyses. I still see it in people's writings, with the drafts that I get of people still saying, hey, my one variable causes change in the other variable, or some wording like that. Make sure in your papers that you don't have any wording like that. Instead, you just say, hey, there's a relationship between the two, where one variable is related to the other, is associated with the other, not causes. So make sure that in your paper, you get rid of any language regarding like this causes this, right? All right, here's another question. There might be one more after this. If there's no relationship between parents' aggression and children aggression, we would expect the correlation to be -1, 0, or 1. All right, good. I'm seeing everyone for the correct answer. Good job. It is B, 0. Seems like I don't have to dwell on that. Everyone who responded got it right. Seems like people understand that now. Good job. All right, these next couple slides, they're just in the PowerPoint, just in case you want to look through them. We talked about these last class. Both the non-directional and directional null and alternative. Not going to talk about these. Here are these slides again on this PowerPoint in case you want to go back and look at them, but they're the exact same slides that we talked about before. Do anyone have any questions about hypotheses for correlations? No, we talked about them before, but do anyone have any questions now that I could answer? Okay. So let's end our conversation with correlations with talking about some limitations of them. Correlations are great. They're a great way to just get some descriptive information about your study, or like some basic information about the variables and your sample, but they do have some major limitations. And this first one is this idea of curvilinear relationships. So correlations only capture linear relationships. And when I say linear, what do I mean? I mean, as one variable increases, does the other variable increase or decrease, or is there no relationship? Just simple linear relationships. As one goes up, does the other also go up or to go down? Simple relationships. But what happens when the relationship between your variables isn't linear? It isn't a straight line, but it's curved in some way. And these are called curvilinear relationships. So let's give a pretty, I'm gonna have a couple examples on these PowerPoint slides, but let's just walk through this first one. So we're looking at the relationship between anxiety and test performance. And this is actually a really real relationship. It's actually rather interesting. And what turns out is there is like a right amount of anxiety to feel, and you'll actually like do better on an exam. So people who feel moderately anxious about an exam actually tend to do the best. They perform the best on whatever, that could be, an exam like a school exam. This is also true with sport performance. A lot of performance like sports psychology deals with this idea. So it turns out that a moderate amount of anxiety is actually good for performance. And then it turns out that if you're not anxious at all, now, of course, this isn't saying that everyone who feels no anxiety going to a test will do bad. Maybe it turns out that you're just in a class that you don't belong in, and it's like 5th grade math, right? And you're like, I got this. I don't feel any anxiety at all. We all have some of those gen ed classes, right? There's no anxiety, you got it. But for the most part, people who don't feel a lot of anxiety tend to do bad. And then as you get more anxious, you do better. But it gets to the point where if you start getting really anxious, performance starts to go down. So if we were to look at this in a linear relationship, there actually would be like no correlation. And I want to show you, I actually made up some data. I do want to show you this in SPSS. So I created just fake data between anxiety and exam performance. And we can see here, actually, someone tell me, is there a correlation? Let's see if I can zoom in. I can't really zoom in, but look at this box right here. Is there a positive or a negative correlation or no correlation between exam performance and anxiety? I can't. Let's see if I can maybe zoom in. Yeah, let me zoom in. Here we go. SPSS wants to be difficult. So in the direct message, tell me, is there a significant correlation between anxiety and exam performance? And if there is it positive or negative? Okay, so I'm seeing answers all over the place here. So let me walk through interpreting. So I highly suggest if you got the wrong answer here, and I'll tell you what the right answer is in a second, but if you get the wrong answer, I highly suggest you go back to the prior lecture, either rewatch it, it's on YouTube, or go through the PowerPoint slides again, where I talk about how to interpret correlation output. So first off, is this significant or not? Well, all we need to go is this SIG row. Let's go over and we look at the correlation between exam performance and anxiety. Oh, okay, it's greater than 0.05, not significant. So we know there is no correlation between exam performance and anxiety, regardless of what this number tells us. This is an important point of SPSS. SPSS will always tell you a numerical value. It will always say, hey, here's a correlation. But remember, the whole point of this significance test is to tell us, okay, there is a 19% chance, right? This 0.19, there's a 19% chance that these results are just some error. So it will always give you a correlation value, but your job is to look at this significance and say, hey, is this greater or less than 0.05? If it's greater than 0.05, it means there's no correlation, regardless of what this number tells us. There is no correlation. These results are completely due to chance. It's an error. This number is an error. There is no correlation. So we can see here that there is not a significant correlation, which means it's not positive or it's not negative. There's just no correlation. All right, so it's not significant. And here's a scatter plot of anxiety and exam performance. So it looks very similar to that PowerPoint that I just talked about, or that I just had up. But we see here there's this curvilinear relationship. That moderate amount of anxiety, people do the best. High amounts of anxiety over here, people do worse. Low amounts of anxiety, people do worse. So I ran some advanced analyses, not going to go into them, but I ran a test that tells us, that looks at it at a linear level and a quadratic level. Once again, you don't need to know this. I'm just trying to show you a point here. This quadratic is this curvilinear. It's the same word. It's just a SPSS term for it. And so we can look at this linear level, let's look at this row, and hopefully you can see it, but we see it's not significant. And it's actually just a correlation, right? It's the same exact correlation we looked at. It's not significant. But now let's run some advanced analyses and let's look at the relationship between exam performance and anxiety at a curvilinear level. And we can see, oh, wow, it is significant. So at a curvilinear level, the relationship between exam performance and anxiety does exist. And it's actually, this effect size is really strong. So we go from there's no relationship at a linear level to wait a second, there is a really extreme relationship between exam performance and anxiety. And actually, here's this graph again. So we can see it plotted out this curvilinear best fit line. And we can see it's what we'd expect, right? What we saw on that PowerPoint. And here's that correlation. There's no correlation here, right? It looks like it's slightly positive, but we know because we can interpret output, there's no correlation. So I wanted to show you that at a linear level, correlations are for linear relationships. For relationships that aren't linear, correlations don't work. They just don't work. And here is, proof of that. All right. So, I showed you a bunch of advanced analyses here. Really, all you need to understand is that correlations only capture linear relationships and not curvilinear relationships. I have a couple more examples of curvilinear relationships. Here's one: amount of beer consumed and your beer pong performance. So some people, have a optimal drinking or drunk level, I guess, if you want to say, that makes them best at beer pong. You don't have any drinks, you're not great. You have too many drinks, you're also not great. An example of a curvilinear relationship. I think we have, no more. Okay, so there's just two. So once again, correlations only capture linear relationships. So let's talk about another limitation of this correlation, and that's outliers. So outliers can dramatically impact a correlation. I just have the definition here, by definition, an outlier is just something that's plus or minus 3 standard deviations from the mean. I'm not going to test you on that. It's just, here it is. So here's some examples, and I have actually some another real life example. But so here we know that without the outlier, if we would take that outlier away, there'd be a strong positive correlation of 0.7. With the outlier, it actually reduces that correlation to 0.4. Here's another example. So without the outlier, right, if we took away this point up here, and we just looked at this data right here, this is a rhetorical question. You don't need to put it in the chat, but is there a relationship? Knowing what you know about scatter plots, is there a relationship or a significant correlation with this data right here? And hopefully you would see this and say, oh, no, the answer is no, right? There's no relationship if it looks like this cloud of data points. But if we were to put this one little point up here, this extreme outlier, it drags that correlation of 0 to 0.85. So a really strong positive correlation. So outliers can really mess with your data. And let's do this again. So here I have, from a previous semester, I have the correlation between classes missed. So I counted up how many classes people missed throughout the entire semester, and their exam 3 performance. So once again, in direct chat, let's do this again. Is it significant, the relationship between classes missed and exam 3 performance? And if it is significant, is it a positive or negative correlation? Can people see this, or do I need to do that zoom in thing again? All right, I'm seeing some answers go in, so I assume people can see it. Okay. All right, cool. So majority of people have the correct answer. It is significant because we know that 0.000 is less than 0.05. And we know that it's negative because just simply the Pearson correlation value is negative, right? All we need to know. So it is significant and it is negative. So let me do these analysis again, right? So I ran this correlation, real data. All I did was I ran it again, but I added 2 data points. I added 2 outliers. So I added one person who did really well. So like they got 100%, but they didn't show up to one class. So maybe they took the class before and they didn't show up to any class, but they still did really well in exam 3. And here I have, and I also added one person who did not do well, but showed up to every class, right? They showed up, but they didn't do that well on exam 3. And so we can see that this correlation of negative 0.5, which is relatively strong, right? That's a relatively strong relationship between attending class and doing well in an exam, or I guess not showing up to class and, and doing worse on an exam. I threw in 2 people who, and I just talked about that. It completely makes this, it makes it not significant anymore. 2 data points. So 40, you can see here, 44 people in these original real data, 46 people in the new data. I just added 2 people who are extreme outliers, and it makes that strong correlation down to nothing. There's no relationship. So 2 data points completely screwed up my correlations. So correlations are really impacted by outliers. So that brings us to this question. It's a thought question. If we were in person, I'd have us like get into groups and talk about it, but I don't want to, take up too much time. So I want you to really think about this, and then I'll ask you for your answer. I'll give you a minute to think. Should we remove an outlier from our analysis? So we have an outlier. We identified there's an outlier. Should we remove it? No, it's real data, right? It is a real data point. It is a real participant. 2, or B, yes, it's clearly an error, right? That outlier is an error. C, maybe, but only if it's causing it to seem like there is a correlation that otherwise isn't really real. Or D, maybe, but only if it's reducing your correlation and it otherwise would be stronger. So think about this for 30 seconds. Should we remove an outlier from our analysis? And throw your answer in a direct message chat, and then I'll talk about what the actual correct answer is. Okay, so I'm seeing most people are split between A and C, and there's a couple D's thrown in there, maybe 1 or 2 B's. And the real answer is it really it matters what type of analyses you're doing, first off. And also, your data the best and your population. So let me walk through and explain. I personally think the answer is C. But I also agree with it's real data. That is a real participant. But sometimes we really truly do get just random things in our participants that causes them to be on some extreme end that, think about what a standard deviation is. Are those people in those extreme ends, so in those tails, at the really low end and the really high end, are those people really representative of the majority of people? No, probably not, right? They definitely represent the extreme ends, but in psychology, we want to maximize, the help that we can do. And we really want to focus on, now there's certain fields where you focus on the extreme ends, like therapists, they can help people who are extremely depressed, right? But a lot of psychological research really cares about the average person, because that's who our research can help, the average person. So while it is real data, maybe we should get rid of them because it's really messing up our data for the average person. It's never an error. I mean, it could be an error. There are instances where, let's say your scale goes from 0 to 10, but one of your participants has a 20. So often, many times it could be an error because maybe you messed up, calculating something. Maybe Qualtrics messed up, whatever. It could legitimately be an error. This is something you as a researcher, you look at your data. And one of the things actually you'll do more in 204 is you'll sit there and you'll really look at the data that you collect and really look at, okay, who should we get rid of? That's not something we talked about this semester. You'll focus more in 204. But in my opinion, the true answer is C, but you should report it both ways. So you should typically, if you're going to delete outliers, like if you're writing a paper, I always talk about, I say, hey, here are the analyses with the outliers, and here's why we removed them. So you just talk about it in your paper. There's always a section in your results section. You may have seen it in the homework. I forget if I took it out or not. But a lot of the times in our results sections or our methods, we talk about, hey, here's who we removed from our data set. And this is where it comes up. And this is one of the reasons why, because correlations can influence your results. So therefore, you need to talk about them in your paper. I won't ask this. This was just a thought question. This won't pop up on the exam, but it is nice to see people thinking about it. And really, you could argue for most of these answers. All right, a couple more. So another limitation of a correlation coefficient is it doesn't tell you if there could be different subgroups or there's things happening in this simple linear relationship. So here's an example. So we're looking at the correlation between shoe size and reading score. All right, and it looks like a positive correlation here. Participants who have higher or larger shoe sizes have a higher reading score. And for the sake of time, I would sit here and I would be like, oh, what could be the possible reason for this? And it could just simply be people who are older, right? Let's say you're looking at elementary kids school, or elementary to high school kids. And people who are older typically read better, right? 12th graders read better than second graders. 12th graders also have bigger shoes typically than second graders. So therefore, that correlation does not imply causation, right? We're not saying that shoe size causes people to be better. There's a whole other explanations for why. Anyways, we could also look at some different age subgroups. So if we looked at, let's say this is just, I don't know, second graders, and this circle is third graders, and this circle is fourth graders, we actually see that if we were to break it up by age or break it up by year, there's actually a negative correlation going on in specific age groups. So with each age group, there's actually a negative correlation between shoe size and reading score, but overall it's positive. So correlations don't get at this. They don't tell you, is there something else going on? Here's another example, the relationship between height and weight. What you'd expect, overall, there's a strong positive relationship. But if you were to break it down into male and female, it turns out that males, moderately positive relationship between height and weight, but females, there's like a really weak positive relationship. Height isn't really related to weight for females. There's like a weak positive, right? But for males, moderately positive. And here's a real world example of this in my own data. I'm currently writing a paper on it. But I ran a correlation between social media addiction and depression for adolescents, for 286 adolescents. And it turns out there's like a weak positive relationship, right? More addiction to social media is related to more depression. Pretty typical. But I broke this up into males and females because I wanted to know, well, I know boys and girls use social media differently. Does it differ? And it turns out there is no relationship between social media addiction and depression in males, right? Not significant. But for females, it's actually a pretty moderately strong relationship. For girls, increased social media addiction is related to depression. For boys, it's not. And actually, if you do some more follow-up analyses, this is what I'm writing my paper on. This is that I think I talked about it before, but lonely boys actually benefit from being addicted. So more addiction to social media for boys who report feeling lonely, it actually was like it benefits them, less depression, higher self-esteem. So more social media is actually better for a subgroup of my population. But for another subgroup, females, it's the exact opposite relationship. So correlations don't get at that, right? When I originally ran that initial correlation, I could come to the conclusion, let me pull it up again. If I was a researcher and I just ran this general correlation, I could say, oh, okay, there's a weak relationship between social media and depression in my sample. But when you really break it down, there's actually a lot of interesting subgroups there's stuff that's going on. So correlations don't get at that. That was the whole big point of that. Correlations, the relationship between X and Y, so whatever your two variables are, may vary across whatever subgroups are in your sample. Okay, here, I think this is the final limitation. Maybe there's one more, but this restriction in range. This is actually a really interesting psychological methods concept in developmental psychology. So maybe if you take some developmental psychology course, like human development, maybe they talk about this. But so let's say we looked across the lifespan, the relationship between just age, so age across the lifespan, and reaction time. And we know as people get older, right, they get slower. We know that. They get slower in a lot of things, and this one is just reaction time. So older people are slower at whatever reaction task we gave them. So if this was a correlation, right, your interpretation would be there's a significant positive relationship between age and reaction time. As people get older, they get slower. Does everyone see how I got that interpretation? As people get older, they get slower. What happens if we were to just look at, 18 to 25-year-olds, right? So these young adults. And what you'd actually see, if you just looked at young adults, there's no correlation at all between age and reaction time. So this is actually a really interesting concept of you have to know your variables, right? Would we really expect 18-year-olds to differ from 25-year-olds in reaction time? Probably not, right? But would we expect 10-year-olds to differ from 70-year-olds in reaction time? Yeah, we would. So this is really about you as a researcher understanding your variables, because I could run a correlation on literally anything I want. I could look at 18 and 25-year-olds, but if I don't expect any differences, there's going to be no correlation. Here's another example, depression. If I were to measure depression, let's look at adolescence. We know during adolescence, because of puberty, because of other reasons, depression is on the rise in adolescence, right? Early adolescence, not as much depression. Late adolescence, potential for lots of depression. And this can go into emerging adulthood, right? Depression can go on for the life. But if I were to measure depression on, let's say I pick a random girl, right? A random adolescent girl. And I measure depression at 8 years old and at 15. Would we expect some differences? Would we expect depression to go up? This is a rhetorical question, but yes, right? We would expect the depression to be on the rise from 8 to 15. Let's say I took that same 8-year-old, right? Or it was a 15-year-old, and I measured depression on Monday and I measured depression on Tuesday. Would we expect any differences? Does depression change day to day like that? No, it doesn't, right? Depression doesn't change. Your mood may change, which may be an indicator of depression. But if I gave you a depression scale, your depression scale should not change much between Monday and Tuesday. So it's all about knowing your variables. If I was trying to assess change in depression, I'm not going to assess people from day to day, right? Or if I'm going to be looking at reaction time, I probably wouldn't expect much of a relationship between age and reaction time from 18 to 25-year-olds, but I would from 0 to 7-year-olds. So this is the idea of really knowing your variables. I don't want to harp on this too much because I'm not going to be asking you in the exam, but as a researcher, make sure you really understand your variables and what you expect versus shouldn't expect. Someone asked the question, should we analyze subgroups to put in your paper? This is completely optional if you want to or not. So you do have the option of um, I I haven't taught you how to do it, but if you did want to look at the relationship, like do girls and boys differ in self-esteem, or do boys and girls differ in the variable that you created? So social media addiction or exercise, because that is one of the things you could assess, right? I'm going to suggest that you don't assess differences in ethnicity, just because the majority of the sample was white. There's not too many peoples to compare that to, but if you do want to analyze different subgroups, come to class on Friday and I can walk through showing how to do an independent samples t-test. It's something that I had up on the PowerPoint. And I think I screwed up and I didn't show how to do an independent samples t-test. But if you are interested in analyzing subgroups to put in your paper, and if you make an honest attempt at it, I'm not going to say that you get extra bonus points, but your grading will be very lenient. I'm not going to take points away. You can only get points added if you make the honest attempt at doing this. But come to class on Friday and I can walk, or even actually not Friday, this Wednesday. Stay after class on Wednesday. It should be a relatively short class. Stay after class and I can talk about analyzing subgroups using an independent samples t-test. So if you are interested in that, just stay after class, the short class on Wednesday, and I can talk more about that. Okay, so let's end this conversation with talking about different types of correlations. For the purposes of the final exam, you are only going to be expected to know how to run a Pearson's correlation. So we talked about a Pearson's correlation is what a typical correlation, and everything that we've been talking about is a Pearson correlation. I showed you how to run a Pearson correlation last class. I showed you how to interpret it and do an APA write-up. So for the purposes of an exam, that's the only thing you'll need to know how to actually interpret and do. But there are different types of correlations that you need to be aware about and that you may be asked about on the multiple choice part of an exam. So first off is this Pearson's correlation. And this is the typical correlation that we've been talking about all semester, but this measures the relationship between two quantitative variables. So age versus health score, IQ, self-esteem, social media, depression, right? Just any variable that varies numerically, like some scale or whatever, just two variables like that. Pearson's correlation. A Spearman's correlation, on the other hand, is a correlation between two ordinal variables. So think about grade, right? A, B, C, D, F. Think about where you finish in a race. There's a logical order, first, second, third. So variables like that, where there is order to them. Here, another example that's not up here is if I had you all rate like how much what's your favorite, rank these from your favorite to least favorite. McDonald's, Burger King, Wendy's, Chick-fil-A, and I gave you a bunch of restaurants and I had you order them from least to greatest. I could compare everyone and see, do people match up? Like is Avery's top restaurant chain, the same as, Justin's top restaurant chain, right? So we could see with these rank order variables, the correlations between them. So Pearson's correlations, just two quantitative variables. Spearman's, two ordinal variables. Quantitative versus ordinal. There's two more correlations, a point biserial and something called like a phi coefficient. So a point biserial correlation measures the relationship between one quantitative variable and one dichotomous variable. So this kind of looks a lot like a t-test, an independent samples t-test. And it actually essentially almost is exactly the same thing. But instead of looking at like group differences, it looks at a correlation logic. So we could examine gender and exam score. We could look at, smokers versus non-smokers and I don't know how fast they can run. Young people versus old people and their scores on religiosity score. And if I was going to ask you more questions about doing the exam, I'd actually walk through some of these correlations with you. But for the purpose of the exam and what you really need to know, A point biserial correlation is just a correlation between a dichotomous variable and a quantitative variable. And then the phi coefficient measures the relationship between two dichotomous variables, gender versus whether you own a cat or not. You'll focus more on this. You'll learn about something called a chi-square test in 204. This is another example. A phi coefficient is a chi-square. So you'll learn more about that later. But I summed it up in this slide right here. Really, what do you need to know? If I could synthesize these past two slides, here's what you need to know for the exam. A Pearson is just two quantitative variables. A Spearman is a correlation between two ranked order variables. Point biserial is one dichotomous, one quantitative. Phi coefficient, two dichotomous. So really, for the purpose of the exam, this is all you need to know regarding those other correlations. And then, of course, you need to know how to actually conduct a Pearson's correlation and interpret that output, but we've already talked about that. All right, so that's it for today's lecture, but don't go just yet because I want to show you what part 2 of the final exam is going to look like. So essentially what's going to end up happening is you're going to have like 45-ish minutes, I believe. I'll double check on that in class. So you're actually going to be here in class. If you don't show up in class, you can't do part 2 of the exam, part 2 of the final exam. Probably going to fail the final exam then. So make sure you're in class. What's going to end up happening is I'm going to give you a data set, right? And this data set's going to have like 6 or 7 variables in it. And these variables are going to range in, some are going to be dichotomous, like gender. Some of them are going to be categorical that aren't dichotomous, like, what's your favorite color? And it looks like there's 4 options here. So some of the things that you're going to have to do is, and I'll give you a Word document with this, so that way you can study, and I'll give you an example data set, so that way you can, run this stuff. But here's what I have created so far, and I'm still working on this. Here's what you're going to have to know how to do. Let me zoom in just a little bit more. So I give you this data set with a bunch of variables, and I give you some information on these variables, right? I say, hey, age is a continuous variable, gender is a dichotomous, 0 is male, 1 is female. I give you information. And what you need to do is multi-parted, but tell me all the different statistical tests you can run with the given data/information. So this may require you to look at the actual data in SPSS, look at the variable view, and understand a little bit more about this data. So if I were to give you this data set, I'm going to get rid of the point biserial. What you need to tell me is how many different one sample t-tests can you run? How many different independent samples t-tests can you run? How many Pearson correlations can you run? So this is going to require you, how many independent samples t-tests can you run? Well, it's going to require you to then to be like, okay, independent samples t-test, I need a continuous variable, right? But then I also need a dichotomous variable to look at the differences between these two groups. So we have one dichotomous variable, and it looks like we have 1, 2, 3 continuous variables. So I could run an independent t-test on gender and self-esteem. So how do boys and girls differ on self-esteem? How do boys and girls differ in depression? How do boys and girls differ on age? Can I run an independent samples t-test on how do boys and girls differ on favorite color? Tell me in the direct message chat, yes or no. Can I run an independent samples t-test on gender and favorite color? Okay, I'm seeing split answers here. So if you got this wrong, I'm going to highly suggest you go back and review these lectures. But the answer is no. We can't run an independent samples t-test on gender and favorite color. Because why? Someone tell me why not. Why can't we run an independent samples t-test using favorite color? What is one of the requirements of an independent samples t-test? You have to have a continuous variable, right? And then you have to have a dichotomous variable that are groups. So we have our groups, we have gender, right? Boys and girls. Favorite color is not a continuous quantitative variable. You can do it on self-esteem, you can do it on depression scores, you can do it on age, but you can't do it on a categorical variable. Yeah, someone said in chat, favorite color isn't continuous. Good job. So how many different Pearson correlations? I'm not going to ask you in chat, but make sure you know how many different Pearson correlations. Some people struggled with this on the quiz. Yeah, but I mean, so just, what's the requirement for a Pearson correlation? We need 2 continuous variables. So I could run a Pearson's correlation on age and self-esteem, age and depression, self-esteem and depression. So these are just some things that you need to know. Now I need to mention, it says open note. This will be an open note section of the exam. However, you're only going to have 30-ish, 45 minutes to do this. So if you don't already know this, or you don't have your notes already written out in a nice laid out, cheat sheet, you're going to struggle a little bit with this. Yeah, so make sure you can identify, tell me how many different of these tests you can run with the given data and information that they give you. It's really going to require you to know what types of data you need to run the different tests. Each test has a slide where we talk about this in some PowerPoint. Then you're going to have to run the following test / tell me the following information. It's going to be a bunch of questions, but I'll be like, okay, what is the mean for this variable? Or what is the median? What is the mode? Is it skewed or not for a particular variable? And you have to be able to know how to run descriptives or frequencies and find that information. Be able to run a one samples t-test. So you need to be able to run it, understand the output, and be able to give an APA write-up of it. Same thing for a Pearson correlation. Run, understand the output, and be able to interpret. Then, I may give you a couple variables from that data set, create directional and non-directional null hypotheses and alternative hypotheses. So, given 2 variables, if I gave you the variables self-esteem and age, give me an example of a directional alternative, right? So that would be one of the questions. And, a directional alternative correlation. And you'd be like, oh, okay, people who get older, or as age increases, self-esteem increases, or as age increases, self-esteem will decrease. Some alternative hypothesis. All right, so I'm going to work a little bit more on this know how to study guide and send this out. It'll be like 2 weeks prior to the exam, as well as an example data set. One suggestion I have is to create cheat sheets. And this is what I did as an undergrad, but I would have an output. So this is an example of an independent samples t-test output, right? This is from the t-test PowerPoint that's up on eCampus. We talked about this a week or 2, whatever ago. But I would have this output up on my cheat sheet, and I would say, then below it, I would have the APA write-up of it with the example output. So that way I could say, okay, where do I find this number? Well, I find it right here in this degrees of freedom. Okay, where do I find this number? I find it right here. Where do I find the p-value? It's right here. And I would do that, I would do that with your correlations, right? With your group correlation. So you have the correct answer. I just have a cheat sheet where you have the correct answer of the output and the write-up. So that way, whenever you have to run, a correlation on age and self-esteem and interpret the output and give me an APA write-up on a final exam, you can just go to your cheat sheet where you have the output already, you have the write-up. All you need to do is change the correct information in and out, right? The correct numbers. That's how I'm going to suggest you create a study guide for this exam or for this part of the exam. Whenever I give you this, just make sure you know how to do everything on here. You have a cheat sheet if you need it, and you'll be just fine. It's open note, so as long as you take good notes or you have, a good cheat sheet, you'll be fine for this part of the exam. Any questions about this second half of the final exam? All right, by the end of this week, I'll have an example data set out to you, as well as a Word document saying everything you need to do. This example data set will be a data set, and it'll have questions that you may find on the final exam. do it and then come to me. I don't have the syllabus pulled up. Let's say we can discuss it next Friday when it's exam 3 review. If you have any specific questions about that part, about this example data set, you can ask me then, or you can ask me at any point before that, but that we'll have a dedicated time then. Other than that, we'll talk more about the final exam next week. But end of the class, have a great day. I'll see you on Wednesday for a shorter class. Feel free to stay after today and ask me any questions about anything. But if you don't have any questions,